Good morning. Myself, Dr. Meenal Gupta, Assistant Professor in Chemistry subject and in Government Arts and Science College, Ratlam, Madhya Pradesh. Under Faculty Development Program, I am presenting a short MOOC online course on the topic of ultraviolet visible spectroscopy under Guru Anand Dev Teaching Learning Center, a center of Ministry of Education under PMMM and MTT scheme, and it is collaboration with Government Madhav Science College, Ujjain, Madhya Pradesh. For preparation of short MOOC ultraviolet spectroscopic course, the objectives here to learn this through online e-content teaching learning process, enhance their outcome, which is based on spectroscopic technique, and this field is useful for beneficial to the UG student, PG student and pharmaceutical students as well as industrial aspects also. And here content is the introduction, theory, and which is based on laws, that is Lambert-Beer law. Different types of electronic transition includes effect of conjugation and applications with examples, and methodology based on interactive e-content learning, which is based on conceptual pictures and animation techniques. Evaluation methodology, generally description about the electronic transition in other parameters, and after followed that we also given here assessment for the students, and we will also provide notes on the basis of UV visible spectroscopy. Firstly, when the sample is interact with the definite light of electromagnetic radiation, the change in specific energy in the compound gives rise to the spectrum. The range of electromagnetic radiation having different types of specific energy is showing here: cosmic, gamma, X-ray, ultraviolet, visible, infrared, microwave and radio wave. This is based on increasing order of wavelength, and the particular wavelength oriented energy is especially used for different types of spectroscopy, and here ultraviolet visible spectroscopy cause the electronic transition in the compound, and the specific range start from ultraviolet 200 nanometer to the 780 nanometer goes to the visible range. Therefore, the ultraviolet range starts from 200 to 400 nanometer, and visible range starts from 400 nanometer to the red wavelength 780 nanometer. Here the UV spectroscopy is a type of absorption spectroscopy. Here already know that 200 to 400 nanometer is for the ultraviolet region, and 400 to 780 nanometer for the visible region is absorbed by the molecule, and it is the specifically absorbed by the specific molecule. Therefore, it is a specific type of transitions of electrons takes place from HOMO to LUMO to give the molecule in the excited state, and we can learn about the absorption spectroscopy. Next is that here what is absorbance. When the light is absorbed by the molecule, then we can calculate how types of absorption here and cause of absorption and what is the absorbance. It is based on again Lambert-Beer law. So it is the ratio of intensity of incident electromagnetic radiation from the source to the reflected electromagnetic radiation, and it is detected by the detector. And mathematically A equals to A means absorbance is the ratio of log of I0 upon IT. I0 is the incident light of the monochromatic radiation, and it is because we have learnt here, reading here the ultraviolet visible spectroscopy. Therefore, the light here required UV visible light range, because this light range required means very high energy, because the energy levels, the difference between the energy levels, energy gap is so high, and it is equivalent to the UV visible light. Therefore, the UV visible light is responsible for the electronic transitions, and all type of molecules give electronic transition. There is no any type of selection rule for that types of molecule. Which type of molecule we can select any type of molecule for taking the electronic spectroscopy. But here the electronic transition when takes place always from HOMO to LVMO molecular orbitals, and always takes place from G to U means unparity, means the if ground state is Girard, then excited state will be un-Girard. Then log I0 upon IT barabar equal to the epsilon CL. Epsilon is the molar extinction coefficient, C is the concentration of the sample, and L is the path length of the cuvette. This whole absorbance and this Beer-Lambert law is the basis of the UV visible spectroscopy, and from this we get ultraviolet visible spectrum, and the absorbance means lambda max. So therefore, which instrument is involved here? Here UV visible spectrophotometer is involved. From that we find out lambda max, wavelength, maximum wavelength, and epsilon is the molar extinction coefficient, and L is the path length of the sample. And A equals to epsilon CL means A equals to log I0 upon IT. So therefore absorbance is equal to the epsilon into C into L. It means epsilon and L is constant, therefore absorbance is directly proportional to the concentration, and absorbance is directly proportional to the concentration. It means it gives a linear relationship. As increases concentration of the solution, absorbance of given sample also increases. It is suppose this is the sample solution, and when monochromatic light passes through the sample solution, that some light was absorbed by the molecule and some are uh, reflected, means transmit light. Then initial light is called the I0 and transmit light is called the IT. So therefore the ratio is the log I0 upon IT is called the absorbance, means how much light is absorbed by the molecule. All these we can calculate it by using this mathematical representation. Then the number one thing is that for knowing about the which types of electronic transition takes place, firstly we require to find out lambda max, then that is the called absorption band. Then the graph is plotted between absorbance and wavelength, and the wavelength may start from like 200 nanometer to 780 nanometer. Then we have here shown that one band is observed, and in any compound more than one bands may be observed, depends on the types of electronic transition takes place in the molecule. And here the maximum absorption, this maximum absorption means maxima, the point of maxima is called the lambda max. Lambda max means wavelength, 8 wavelength where the absorption is maximum. So this is the lambda max, this wavelength correlated to lambda max where the absorption is maximum. After find out lambda max, we can calculate the second point. We here will form the calibration curve, standard or calibration curve. For given sample, we form the calibration curve, and calibration curve is plotted against absorbance versus concentration, and at different dilution of the concentration, we have obtained a linear relationship, that is absorbance is directly proportional to the concentration. But Beer-Lambert law is applicable only in very dilute solution. Very high concentration it gives non-linear relation, means it deviates from linearity. After that find out linear relation, we can take a sample solution which have a known concentration. Therefore, we take direct absorbance from spectrophotometer. In this range, the point of the absorbance will be give the concentration of given sample. Then the theory of the electronic transition is based on that molecular orbital theory, and in case of molecular orbital theory, atomic orbitals are joined together, linearly combined to form different types of molecular orbitals, and the electronic energy level of that orbitals are sigma is lower, then pi bonding, then non-bonding, then pi anti-bonding, and then sigma anti-bonding. Then the electrons are filling in the low order of increasing energy of orbitals, means firstly they have filled in low energy, then increasing order of energy. Okay, then the here what about the HOMO and LUMO? HOMO is the highest occupied molecular orbitals, that will be bonding molecular orbital which have highest energy, and LUMO will be anti-bonding orbital, or maybe say non-bonding orbital, maybe anti-bonding orbital which have the lowest unoccupied molecular orbitals, means very lowest and which has unoccupied molecular orbitals are showing here, that is the LUMO. It means when electronic transition takes place, then it always follow the electrons from jump from HOMO to LUMO, means highest occupied to lowest unoccupied. Just like when we study in our class, then we go to first class, then second to third, third to fourth, then third to fourth, third is HOMO and fourth will be LUMO, like that. Then types of molecular orbitals are bonding molecular orbitals, which have low in energy, non-bonding molecular orbital which has same energy, that is the atomic orbital, and anti-bonding has highest energy orbitals. Okay, then this is the energy distribution of the orbitals, and next the transitions in molecular orbitals. Okay, after filling the orbitals in increasing order of energy, that follows above rule, Hund's rule, and then when we give the electromagnetic radiations of ultraviolet or visible range, then molecules depend on its electronic contribution, its skeleton, then it absorbs a specific definite light of energy, that is called quantization of energy, and that is responsible for the electronic transition from HOMO to LUMO. It is based on the depend on molecular energy. If molecule is non-bonding orbital, then non-bonding to any sigma star anti-bonding या pi anti-bonding electronic transition takes place. If molecule has pi bonding, then electronic transition takes place pi to pi anti-bonding. So there are the possibility here, different possibilities arise, like this is sigma bond, this is pi bonding level, this is non-bonding level, pi anti-bonding level, and highest energy sigma anti-bonding level. Then sigma to sigma anti-bonding electronic transition is required very high energy. Then sigma to pi anti-bonding orbital excitation is required low energy, and N to sigma star is means a non-bonding to sigma antibonding. This is the energy criteria, and non-bonding to pi antibonding. This is required low energy gap because low energy is required here, and here pi to pi antibonding electronic transitions. Therefore, in out of these, the non-bonding to pi and antibonding orbitals, the difference is very low, energy gap is very low, therefore energy is required very low, and energy is inversely proportional to lambda wavelength. It means if here energy gap is low, it means wavelength give rise to higher wavelength. It means which absorption band is goes which absorption band goes to higher wavelength, then N to pi star, non-bonding to pi star goes to higher wavelength. Then the energy order of different types of electronic transition is as follows, like the sigma to sigma antibonding required very high energy, then non-bonding to sigma star low, and pi to pi antibonding very low, and lowest is the non-bonding to pi antibonding. When electronic transition takes place, then number one thing HOMO to LUMO, number two thing selection rule is that Girard to un-Girard electronic transition is possible only, then sigma bonding is un-Girard, then sigma anti-bonding will be Girard, like that. But N to pi star transition is forbidden transition, therefore its absorbance is very low. This phenomena is studied under Beer-Lambert law. Just I give one example here, like that one is chlorophyll. Chlorophyll A, you all know about that chlorophyll. Chlorophyll is a green pigment found in the green leaves, and it is responsible for photosynthesis process, making the food in the plants. Okay, then chlorophyll has green color pigment. And why green color pigment? Because it absorbs violet orange wavelength of the light region, and violet orange, it means absorption will be give the complementary color of the molecule. So if it absorbs violet and orange color, we see complementary color, that will be green color. And here that is the molecule alternate alpha beta unsaturated cyclic ketone. It is ketone, and here alpha and beta position double bond. It means alpha beta unsaturated ketone. And in this case, two types of bonds are present, three types of bonds are present. Maybe say one is sigma bond is present in all type of molecules, and here pi, C carbon carbon pi bond also present, here carbon oxygen pi bond also present, and one thing is more here, that lone pair of electron present on oxygen atom, and therefore now lone pair means non-bonding electrons. So therefore here non-bonding electronic transition also possible. So two characteristic absorption bands here possible when we take the graph between absorbance versus wavelength. Then we see two types of absorption band obtained here. One is pi to pi antibonding transition, means pi bonding to pi antibonding due to presence of pi bond in the molecule, and it has highest more intense band because absorbance is very high, because it is allowed transition. And second one is non-bonding to pi antibonding transition. Non-bonding because oxygen has lone pair of electron. So by use of this spectroscopy, we can help us elucidate the structures, skeleton structures, which type of bonding present in the molecule. Because N to pi transition, it is forbidden transition, has less intense transition compared to pi antibonding, and goes to longer wavelength because energy gap required very low. So therefore non-bonding to pi antibonding transition means any heteroatom like oxygen carbonyl compound present in the molecule. Okay. Then if we find out different types of molecules, if we take examples of different types of molecules, then sigma to sigma antibonding types of transition present in all molecule. Why present in all molecules? Because all molecules possess sigma bond. No anyone molecule formed, and no any sigma, no any compound having that anyone not sigma bond, because all sigma bonded molecule frame the molecular framework. Therefore all molecules show sigma to sigma antibonding transition, but it is negligible because all molecules show, number one, all molecules show, and number two, sigma to sigma antibonding transition when takes place in the far UV region, like not under the range of 200 to 780 nanometer. Second is the non-bonding to sigma antibonding electronic transition. At this condition, where non-bonding means any heteroatom contained the molecule है ना. तो any heteroatom like oxygen, like halogen, like nitrogen, like sulfur if present in the molecule, it means molecule have non-bonding electrons and also present sigma bond. Therefore it give, मतलब all molecule like that give sigma to sigma antibonding as well as non-bonding to sigma antibonding electronic transition. And if molecules has pi to pi bond in the molecule, like alkenes, polyenes, ketones having carbon double bond, carbon oxygen double bond, carbon sulfur double bond, then pi to pi antibonding electronic transition also takes place with sigma to sigma antibonding transitions, like alkenes and ketones. And if molecules having pi to pi bond also, but also the non-bonding electrons like the oxygen or nitrogen, and having pi bond also, then one more electronic transition possible here, that is called non-bonding to pi antibonding electronic transition. Example like that ketone, because it has oxygen, okay, and non-bonding has no antibonding orbitals, so therefore non-bonding is HOMO, then and then LUMO will be pi antibonding because it is vacant and having lowest energy difference. Therefore N to pi star transition possible in that type of molecules. So by use of help of this UV visible spectroscopy, we can elucidate the structure based on skeleton, which bond framework, or which type of electrons involved in bonding. Next, we see here oxychrome and chromophore. All you know about that compounds are color. Some compounds are colored, and we have seen in our daily life, like chlorophyll colored compound. Like if you see in the practical laboratory, then hexa aquo titanium 3 plus. The aqueous solution is colored violet colored solution. Chromophore, due to charge transfer spectrum, it is violet colored. Okay, so the colored property is responsible in general in this type of compounds due to presence of chromophore and oxychrome in the molecule. What is the difference between oxychrome and chromophore? Then oxychrome are chromes are those type of groups which possess chloro, hydroxo, amino, alkoxy type of groups present in the molecule, like maybe say heteroatom present in the molecule, maybe chloro, maybe oxygen containing, maybe nitrogen containing, maybe sulfur containing. And if all these types of group present in the molecule, they have non-bonding electrons. Therefore they are responsible for deepen the color, enhance the color due to presence of oxychrome. Okay, and chromophore, chrome means colored and phore means bringing the compound. So if the molecules have some types of specific functionality present in the molecule, like nitro group, like C double bond C or alternate double single bond or ketone or nitro or cyano or benzene like molecule, then they are responsible for the colored compound and they are called chromophore. Okay, then chromophore plus oxychrome compound should be in the colored property, showing the color property. And as increase the number of chromophores, colored property will be increases. In general, when we see about the types of spectroscopy and types of electronic transitions, we have here also we will see here that there are four types of shiftings are possible in the molecule, depends on the structure of the molecule, like the when we plot the graph absorbance versus wavelength, then the types of shifting takes place here. We have seen firstly the maximum absorption, that is the maxima, that is called lambda max. And lambda max, this lambda max is maybe shifted towards higher wavelength. Higher wavelength means red region, red light. Red light has about 700 to 780 wavelength range of light. Okay, so longer wavelength is called the when the absorption band is shifted towards longer wavelength, then this type of shift is called bathochromic shift. Just I will give example here like benzene and nitrobenzene, and when we go trinitrobenzene or trinitrotoluene, then color will be enhances, the absorption band will be shifted towards bathochromic shift, like picric acid, trinitrophenol, picric acid. In trinitrophenol, here if we see trinitrophenol OH is oxychrome and 3-nitro group is are chromophore. Therefore, it is responsible for bathochromic shift. And when absorption band is shifted towards lower wavelength, then it is called hypsochromic shift. And when absorption band shows high intense absorption band, means deepen the color, intensity of color will be increased, absorption increase means goes up to maxima up, then it is called hyperchromic shift. And when this up absorption band down in the low the color intensity, low the intensity of absorbance, then this is called hypochromic shift. Then after the shifting, types of shifting, the topic I am starting here, what is the effect of conjugation on UV visible spectroscopy. So number one thing is when pi to pi antibonding, sigma to sigma antibonding orbitals electronic transition takes place, then after that if a molecule having extent of conjugation like double single are having different types of chromophore, having they are also increase the conjugation, then therefore the absorption band is shifted towards longer wavelength, and this type of shifting is called bathochromic shifting. I will give here example, and I am giving like that when we plot the graph absorbance versus lambda wavelength, different wavelength, then one we are seeing here 1,3-butadiene. Okay, 1,3-butadiene has lambda max 217 nanometer. Okay, and having two alternate double bond. But when we take example, another second example, 135 hexa triene, then 135 hexa triene having lambda max 260 nanometer. And 260 nanometer means here lambda max increases the value of absorption band and it goes to right side, means red shift. Okay, so this type of shift is called the red shift. And why is called, because why is so, because conjugation or extent of conjugation shift the absorption band towards longer wavelength, that is called rate shift. Why? So because conjugation, when conjugation increases, the difference between HOMO and LUMO will be decreases. Suppose here conjugation is very low here. Okay, then what will here, this and this one the HOMO and this one the LUMO. But when conjugated molecule, then conjugated molecule the energy gap will be low. HOMO up and LUMO down, and the difference between HOMO to LUMO will be low, like that, and therefore the energy will be energy will be down. This line, this gap will be low. Daily, that is the quantization of energy daily equals to h nu. Here energy gap low and here energy gap large. Next example here, conjugation. Example of conjugation. Here we have taken the molecule ethylene, and ethylene have one pi bond. Therefore, two atomic p orbitals combine together to form two pi molecular orbital. One is pi bonding and second one is pi antibonding. Electrons are filled in pi bonding and pi antibonding will be vacated. Therefore, electronic transition takes place here from HOMO to LUMO, and jump by absorption of definite amount of energy, the gap between the equivalent to the HOMO to LUMO. Okay, and this type of electronic transition required very high energy, because here conjugation is not present in the molecule. But when we take 1,3-butadiene having 4 pi molecular orbitals, psi1, psi2, psi3, psi4, and 2 are bonding and other 2 are antibonding, 4 pi electrons are filled according to Above and Hund's rule, and the difference between which one is HOMO, psi2 is HOMO. Why psi2 is HOMO? Because it has highest energy molecular orbital occupied. And out of this, which one is LUMO? This psi3 is LUMO because it has lowest energy unoccupied molecular orbital. So therefore difference between both these will be low than this one. And this is the example of H2. This is the sigma bonding, sigma antibonding. The energy gap will be here, and the definite amount of energy is matches with this. The electronic transition takes place, and this is required energy about 258 kilocalorie per mole. 111 nanometer means the range of far UV. The next example is ethylene, then butadiene, and I have taken next example is 135 hexatriene, but again it is elaborated ethylene, and this is HOMO, this one is LUMO, or 165 lambda max here, and here 1,3-butadiene lambda max found here, okay, either 217 nanometer, increase here. And the next example is 135 hexatriene. This one is here a 1, 2, 3 pi bond alternate conjugation, and 6 carbon atoms, 6 atomic orbitals combine to give 6 molecular orbitals by linearity, and psi1, psi2, psi3 are filled, psi4, psi5, psi6 are vacated. Okay, and the difference, this one is psi3 HOMO, psi4 LUMO, the electronic difference between both this will be low, and therefore it is shifted towards longer wavelength, that is the lambda max 258 nanometer, but again it is in ultraviolet region, not in visible region. Therefore the compound again it is colorless, and this is the electronic transition, pi to pi antibonding. The next example, the effect of polarity of solvent. So when we take the sample in solvent and dissolve the compound in solvent, the polarity also affect the electronic transition, types of electronic transition. Like if we take here n to pi electronic transition, then what will be see here? We see here that the polarity low polar hexane and high polar uh, like alcohol and water. Then low polar enhance the intensity of transition, and pi to pi star uh, down the intensity of the transition. And here it is the instrumentation technique, double beam spectrophotometer. It is light source that gives the light, and after passing lens and grating it gives monochromatic light, and this monochromatic light passes through double beam spectrophotometer, means through reference sample, that may be the blank, maybe say blank, maybe water, or maybe the solvent which is required for making the solution of the sample, and this is the test sample. Both the light passes through and transmitted, and after that detector to detect the and record in the recorder like that, and we can find out absorbance of different types of the solution or simple solution of different concentration. Next example application. The application of ultraviolet visible spectroscopy is generally to identify the skeleton of the compound, which type of framework present between the carbon-carbon, carbon-oxygen, carbon-sulfur atom in the molecule, maybe sigma bond, maybe sigma to sigma antibonding transition takes place. Then different types of carbonyl group, maybe cyanide group, maybe amine group, and all the types of conditions is helpful for beneficial to the identify the organic or inorganic sample in the molecule in the form of solution, and it is used to find the concentration of unknown solution. We can we can find out the concentration of given sample. For concentration of given sample, what will we do? Then I explain here after 2 minutes. And we can study about geometrical isomers, because cis and trans isomers have different lambda max. By using this study, by use of Woodward-Pfizer rules, we can calculate lambda max for polyenes and alpha beta unsaturated carbonyl compounds also. And we can elucidate the structure of chemical and biological and pharmaceutical samples, and quantitative analysis also we have done using the Lambert-Beer's law. And the for application of UV visible spectroscopy, how we determine the concentration of given sample. The first step is, when we have the sample, first step is find out lambda max. Lambda max, find out for lambda max, we have taken the sample solution very dilute, and we have in spectrophotometer we start from 200 to 800 range nanometer all absorbance, and when we plot graph between absorbance versus uh, wavelength, then we have find out like that, like that. Then this is the absorbance, highest absorbance at that wavelength. This is the wavelength here. Then it is called lambda max, and here is the absorbance. So first step is that find out the absorbance. Second step is that after find out absorbance, we have prepare the 8 to 10 dilution of the stock solution, very dilute solution, and after that dilution takes place around in 10 sample, and after dilution we have find out lambda max. At that lambda max, suppose we have find out like 500 nanometer, then at 500 nanometer we have taken different absorbance of different concentration of the solution at fixed lambda max, like first sample, then second sample, then third sample, and then fourth, and like that 10 samples. Then we plot the graph between absorbance and versus concentration. Very dilute solution, has very low absorbance, very as increases the concentration, so the absorbance also increases like that. And when we match the this points, we have obtained a linear relation. Some points may be up and down, but maximum 3 4 5 points will be in the line. This is linear relation. And after that, third stage is the unknown sample concentration we will taken. And after take this solution, direct we will observe uh, absorbance at this 500 nanometer wavelength. Suppose this is obtained here, यहाँ आई ये, then by intersect this point we have obtained concentration of the solution of given or unknown sample. At that point we calculate the concentration. Then assessment for the students also. So first question is, which absorption band is shown for longer wavelength? For longer wavelength means bathochromic shift or longer wavelength. For longer wavelength, which type of means non-bonding to pi star, pi to pi star, sigma to sigma antibonding, n to non-bonding to sigma antibonding. Then the energy gap in all of four, which is lowest, which is responsible for longer wavelength. The answer is non-bonding to pi antibonding. Which has highest energy in the following? Highest energy range. Okay, then cosmic, gamma, X-ray, ultraviolet, CG, U, V, I, M, R is the order of increasing wavelength. Then the order of increasing wavelength means decreasing energy. Then therefore ultraviolet radiation, that is 200 to 400 nanometer, is responsible for the highest energy.